To snarf something is to eat it quickly or greedily. The Merriam-Webster dictionary traces this slang term back to the early 1960s, a simple blend of the words snack and scarf. But in computer science, this word describes a specific solution to a structural problem. Whenever multiple independent agents communicate over a single shared channel, they have to constantly compete for state awareness. Whether data is moving across the microscopic copper traces of a silicon motherboard or broadcasting through the 2.4 GHz radio frequency band, devices must continuously snoop each other's traffic just to stay synchronized. This continuous monitoring, this snooping and snaffing of packets in transit, is an inevitable consequence of shared medium architectures. If you eliminate the ability to intercept the data, you break the system's ability to communicate entirely. We can examine this behavior in two distinct environments. The first is the microarchitecture domain, where multi-core processors rapidly exchange data over a local bus. The second is the wireless personal area network, or WPAN. This is where smartphones and peripherals form ad hoc, short-range connections known as a Bluetooth piconet. The exact same mechanism of opportunistic data capture exists in both of these domains. The difference lies entirely in the outcome. Inside a processor, capturing data off the bus is a highly optimized efficiency mechanism. Over a wireless network, it manifests as a critical vulnerability in the object exchange protocol, an exploit known as blue snarfing. Data interception itself is computationally neutral. It only becomes a vulnerability when an architecture assumes trust in an inherently untrusted environment. To see how this works at the hardware level, we look at the modern multi-core CPU. Because several processor caches share a single main memory bus, they require a coherency controller to track the most current version of any given file. Engineers manage this using snooping protocols, which fall into two categories: Write-Update, where every change is broadcasted continuously, and Write-Invalidate, like the standard MSI or MESI protocols. This diagram shows a 3-node CPU architecture using Write-Invalidate to reduce bus traffic by telling cores to mark copies invalid. When node 1 attempts a write miss, it broadcasts a read request. Controllers process this using 3 cache line states: valid, dirty, and shared. Without this strict coherency protocol, parallel processors would operate blind, continuously overwriting and corrupting our shared data structures. To resolve a dirty state, Node B pushes updated data directly onto the bus for Node A. The main memory controller opportunistically grabs a copy out of transit, the hardware snarf. Both cache lines then immediately transition from dirty to shared. By snarfing the data off the wire, the system eliminates redundant write-back cycles and makes high-speed multi-core processing viable. But there is a physical limit to this design. As you add more processing cores, forcing every single node to monitor every single bus transaction creates severe power drain and introduces latency-inducing cache access races. To mitigate this, engineers implement a Snoop filter. This directory-based structure monitors coherent traffic, intercepting and pruning broadcast lines before they ping every cache. Inclusive filters track the presence of specific cache blocks, while exclusive filters monitor their absence. When a shared medium scales past its baseline efficiency, engineers implement explicit state tracking directories to physically isolate the unneeded broadcasts. Now look at what happens when that shared medium loses its physical boundaries. A Bluetooth piconet operates as an ad hoc wireless network in the 2.4 to 2.4835 GHz ISM band. To manage traffic, it uses frequency hopping spread spectrum, transmitting data by rapidly hopping across 79 separate channels, 1,600 times per second. This constant hopping gives the illusion of security, but it was designed strictly to avoid radio interference. The pseudo-random sequence is easily calculated using cheap, off-the-shelf hardware. This brings us to the Object Exchange, or OBEX protocol. It is the application layer responsible for transferring files and contacts between paired devices. If OBEX lacks strict authentication policies, you get blue snarfing. An attacker sitting 10 to 15 meters away can scan for devices left in discoverable mode, identifying phones broadcasting their availability. Using specialized tools like blue diving, the attacker bypasses the initial pairing process by brute forcing weak or default pins common in legacy systems. The underlying mechanism here is the exact same hardware snarf we saw on the motherboard, but instead of a main memory controller grabbing data off a copper trace, an unauthorized laptop is grabbing private emails and contacts out of the open air. You can physically prune traffic on a localized copper bus using a Snoop filter. You cannot stop radio frequency waves from broadcasting into the surrounding room. This chart diagrams the modern Bluetooth protocol stack, highlighting the specific mitigation mandated by NIST Special Publication 800-121. For Bluetooth 4.1 and 4.2 devices, the recommendation is strictly Security Mode 4, Level 4, known as Secure Connections. Secure Connections requires two components to eliminate snarfing. The first is 128-bit encryption utilizing the FIPS-approved AES-CCM cipher. If an attacker grabs the packet out of the air, they only see mathematical noise. The second component is authenticated pairing using P256 elliptic curve Diffie-Hellman key exchange. The two nodes use the open, easily snarfed channel to trade public keys, allowing them to independently derive a shared secret that an eavesdropper observing the entire exchange still cannot calculate. Because open RF mediums inherently lack physical boundaries, system security has to abandon the idea of physical obscurity. It relies entirely on mathematical access control. The act of capturing a broadcast from a shared medium is computationally identical, whether it's executed by a silicon memory controller on a motherboard or a malicious laptop in a coffee shop. Hardware architecture manages this by utilizing inclusive and exclusive Snoop filters to physically verify and trust local node states. Wireless architecture manages it by utilizing cryptographic standards like ECDH and AES-CCM to enforce a strict zero-trust model over the air. As our systems scale from enclosed microscopic circuitry to global Internet of Things networks, the foundational challenge of the shared medium remains exactly the same. System integrity is never guaranteed by the mechanical transmission of data. It is guaranteed by how rigorously an architecture defines, verifies, and enforces trust.